Schoenberg type correspondence. And this is a joint work with my advisor, Professor Uwe Franz, and Professor P.V. Rajaram Bhatt. So we briefly recall some definitions, basic definitions of K positive and K superpositive. So we call that a linear map from a matrix algebra Mn to Mn is K positive if the augmented map identity K tensor T from Mk tensor Mn to Mk tensor Mn is positive, and it is called completely positive if it is K positive for all natural number K, and in that case we can write this in the Krauss representation from this. Any completely positive map can be written like this, and we call a linear map from Mn to Mn K superpositive if it admits a Krauss representation of this form such that the rank of Li, this matrices Li, so its rank of each such matrices is less or equals to K. So in that case we call it K superpositive. So it can be easily verified that they form a closed convex cone which are pointed and which has a non-empty interior and which are stable under composition of operators, and they have this chain of inclusion, the one superpositive being the smallest cone and just the positive operators such as this being the cone, this being the biggest cone, and completely positive maps is there. The cone of completely positive maps is lying somewhere in between, and moreover they have this they are connected by this duality relation. If we equip the space with the Hilbert-Smeaty net product, then we have that the dual of the cone of K positive operators, these are K superpositive operators. So this is a bit pictorial representation. So this is the biggest cone of positive maps, and then we have these gradually decreasing cones, that is K positive, then somewhere in the middle K completely positive, and one superpositive being the smallest cone. So the motivation of this talk is by Lindblad's theorem, or also known as Lindblad-Gorini-Kosakowski-Sudarson's theorem, or also known in quantum information Lindblad's master equation, which actually describes the generator of completely positive maps, semigroup of completely positive maps. So it's a famous theorem which says that a semigroup of maps which can be written as exponential T phi will be a completely positive semigroup on the matrix algebra MNC if and only if the generator has this explicit form, this Hamiltonian part and this another dissipative part here, and so here H is an Hermitian matrix and some another matrices. So the motivation of the present talk is that whether we can say something like this about this semigroup of K positive or K superpositive operators. Like can we characterize the semigroup of K positive operators or K superpositive operators in terms of their generators? So this is the question we are interested in. We want to characterize the semigroups of K positive and K superpositive maps in terms of the generators. So more generally, we are interested in the semigroup of characterizing the generator of a semigroup of operators which leaves a cone invariant. So here we can think of the positivity means that some elements is belonging to some cone in some space, and in that case we say that this element is positive. So we are interested in the semigroup of operators which are leaving this cone invariant under this operation. So these questions were a bit answered by Snyder and Vidyasagar. So they got this result that if C be a closed convex cone inside Rn, and we define the dual cone of that, also all these elements of Rn such that this inner product with the elements of cones are positives. So we define it the dual cone in that way. Then for an n by n matrix A, the semigroup generated by A leaves the cone C invariant under this action if and only if this Ax, inner product of Ax and Y is positive for all such pair xy belonging to C cross dual of C with their inner product being 0. So they called it something called cross positive matrix. And Schurman actually mentioned this result in his paper, and he called this kind of correspondence Schoenberg type correspondence, which goes back to classical results of Schoenberg's on a positive relation between positive and negative kernel. So now we come to another version of this, another attempt to this question by Schurman. So Schurman did it for answer this question for Banach algebra with unit. So let's suppose that A is a Banach algebra with unit 1, and A prime be its topological dual, and we consider a cone, convex cone inside A, and we take the dual of that cone, which is defined as all the dual elements which leaves these cones positive. So we say an element A of this Banach algebra A, denoted by small a, is conditionally positive on the dual cone if and only if for all dual element phi which satisfy this phi 1 is 0, we have this this phi takes the the element A to a positive quantity. So this is just the condition of positivity, but with the modification that phi 1 is 0. And Schurman proved this result that if A is a real Banach algebra with unit 1 and C is a closed convex cone with non-empty interior, such that for any element C inside that cone, it is stable under the taking powers for n greater or equals to 0. So that is for n equals to 0, we have this identity. So this unit 1. So the cone contains the unit. Then for an element A, the following statements are equivalent, that A is conditionally positive on the dual cone. This is equivalent to saying that the semigroup generated by A is positive on the dual cone, that is exponential Ta, it belongs to C for all time greater or equals to 0. Now, so but the issue is with this theorem that we are interested in some cones which are important for the quantum information, like K positive and K superpositive, but not all semigroup of operators start with identity. For example, a semigroup of K superpositive operators, it doesn't start with identity because identity is not a K superpositive operator. So this is the issue, that semigroup of K superpositive map cannot start from the identity. So we have to get a version of this Schurman's result which is non-unital, which doesn't we want to prove something similar on the real Banach algebra, but we do not assume that it's a unital Banach algebra. So briefly we recall something of non-unital semigroup. So consider a semigroup of linear operators, this capital T with the suffix in the small t, on some Banach spaces, say V, or in practical purpose, we will do on finite dimension actually. So which do not start from the identity, but we have, due to this relation, this Ts times Tt will be Ts plus T. It imposes the conditions that at time 0, if it is not identity, it has to be an idempotent operator. So if we decompose this Banach space as the image of T0 and the kernel of T0, then we can write these semigroups as the submatrix of tilde T 0 0 0 0 rest of the places, such that tilde T it is a linear operator on the image of T0, and at the time T0, at the beginning, this T0 will be the identity on the image of T0. So now the thing is that if the T0 is a conditional expectation on to some subalgebra of Mn, then we can just study these semigroups. We can just study the semigroup tilde Tt, and that will be enough for us. But the thing is that it's not always the case that T0 will be conditional expectation onto some subalgebra. So in that case, the image of T0 can be just a linear subspace of Mn. So we need a non-unital version of the Schurman's result for that case. So here comes our result, which generalizes Schurman's result, that say A be a real Banach algebra, and we assume there is a cone which is closed convex inside this real Banach algebra A with non-empty interior, and let A0 be a idempotent element. So we are forgetting that A is unital. So let A0 be an idempotent element such that for any element C, we have this product A0 C A0 is still again inside the cone. And we assume further that, as Schurman in the Schurman's theorem, that this C is this undertaking the power is stable, but of course n starts right now from 1, because we are not taking unit here. Then for any B of this element of the Banach algebra which satisfies this commutation, the B A0 equals to A0B, it leaves invariance that is equals to B. The following statements are equivalent. That is, B is A0 conditionally positive on the dual cone C. That is, for all elements of the dual cone which verifies that phi A0 is 0, it leaves B as it maps B to a positive quantity. This is equivalent to say that this semigroup exponential A0 TB, which we define in this manner, this limit n tends to infinity A0 plus TB over n power to the power n, it is again inside this cone C. So this is the non-unital version of the Schurman's result, and with that result we can now apply this result for the all of the practical purpose of the questions of quantum information. For example, if we take A to be the Banach algebra of all linear map from Mn to Mn which are herbaticity preserving, and we take this C to be any of the cones like 1 positive, completely positive, K positive or K super positive, or even maybe I didn't define it here, but maybe entanglement breaking cones. Then if we just fix an idempotent element inside the cone, and then for any psi in this algebra which verifies this relation that psi compass phi 0 is sorry, there is a mistake here, so it will be psi compass phi 0 equals to phi 0 compass psi equals to psi. The followings are equivalent, which says that this semigroup exponential phi 0 of t psi defined in this way, that's phi 0 plus this infinite series. This belongs to the cone for all time t0 if and only if the psi is phi 0 conditionally positive on the dual cone. That is, we have we have this for any element of the dual cone such that this scalar product v and phi 0 is 0. It implies that this product is actually positive v and psi. So in particular, so for example, if we take the cone to say to be k positive, then we can actually characterize the semigroup of k positive maps. But here we have used an identification of two spaces. We can identify the linear maps from Mn to Mn with this Mn tensor Mn star or Mn tensor Mn op. Like in this manner, if A and B are two matrices in Mn, then we define this map TAB by TAB acting on a matrix X by this multiplication AXB. Then it can be shown easily that this map actually extends to an unique isomorphism between this Mn tensor Mn op and all the linear maps from Mn to Mn. Okay, so we can identify A tensor B with TAB, and this gives an unique isomorphism, even a Hilbert space isomorphism. So you can use this isomorphism to get an expression for the identity. So that is just T I cross I or I tensor I. Then as we know, the dual cone of k positive map is k superpositive, so that becomes all the convex all the maps which are inside the convex hull of T V tensor V star, where V is a matrix of rank less or equals to k. As you recall that k superpositive is a linear operator which has Krauss representation such that the Krauss matrix has rank less or equals to k. So basically that's what is written here, and then we just translate all the conditions here. We translate the conditional positivity in terms of in this situation. So it translates to the fact that this product of TV tensor V star times identity, which is just the square of trace of V star. Trace of V, and this is 0. So the conditional positivity it translates to the fact that trace of V is 0, and then this condition here that this semigroups exponential phi 0 t psi, which is defined like in this way, it can be translated with the phi psi identified with Ts, where S is some operator is this AI tensor Bi from Mn tensor Mn op, and the entire theorem here, it can be translated to the fact that this Ts with S like this, it generates a semigroup of k positive maps if and only if the rank of V, which is less or equals to k of course, and the conditional positivity which says the trace of V is 0, it implies that this expression here is positive. Okay, so we can use this result here that we are identifying A tensor B with this TAB to get a nice basis for LMN all the linear maps from Mn to Mn. That is, if a Bi are some orthonormal basis of Mn, then Bi tensor Bij becomes an orthonormal basis for Mn tensor Mn op, and then obviously then this Dbi Bj, this becomes an orthonormal basis of this linear space, linear maps from Mn to Mn. So because this becomes a basis, so any linear map phi, it can be written in terms of the basis decomposition. The basis decomposition with respect to the basis here, and we get as a coefficients of the basis decomposition, we get n square by n square matrix Dij, and it can be shown that this map phi is completely positive if and only if this matrix here, n square by n square matrix Dij, is positive semi-definite. And in particular, so if we take the Pauli basis, Pauli matrices, which forms an orthonormal basis of 2 by 2 matrices, this M2, the M2C. So in that case, if we use this decomposition, then we can actually try to characterize all the positive semigroups on the matrix algebra M2C. So we use these Pauli matrices to decompose phi. So we get this coefficient matrix, so 4 by 4 coefficient matrix dpq, and for any matrix V on this matrix algebra, sorry, so this will be for here, this n will be 2. So for any 2 by 2 matrix V, if we just decompose it in terms of the Pauli basis, so we can show that easily, we can verify that this matrix will have trace 0 if the first coefficient is 0, and it has rank 1 if the square of the first coefficients equals to the sum of the squares of other coefficients. Then we can use the characterization that we have showed for k positive semigroups under this situation to get a nice characterization for positive semigroups on the on matrix algebra M2C, which says that a semigroup exponential T phi on M2C is positive if and only if the 4 by 4 matrix TPQ, this coefficient matrix, is Hermitian, and for all these triplets, these 3 complex numbers, which verifies the square of the sum is 0, we have that this matrix, this submatrix is positive. That is this 3 by 3 matrix. It's a 4 by 4 matrix, and here it's 3 by 3 matrix is positive on all such elements of C3. And we can also characterize the completely positive semigroup of completely positive operators. For example, if we just take any basis Bi of Mn, which verifies these conditions that we start with identity maybe, and then the trace of each such basis is 0 except maybe at the identity, then we can decompose the linear map in a similar way, and we get this coefficient matrix Dij, and such basis always exist, so there is no worry about that. Maybe if you know this well operators, nice error basis, so there are a lot of examples for such basis which can be helpful here. So such bases exist, and we can decompose any map from Mn to Mn in like this, and we get this coefficient matrix Dij. Then we can apply this corollary for this characterization of k positive map to get this conclusion that this semigroup exponential T psi is completely positive if and only if this submatrix here, not this submatrix, this the full matrix is Hermitian for any element, is Hermitian and is positive on any element like this. So it basically says that is this matrix here, the submatrix n square minus 1 times n square minus 1 submatrix is positive on any element of C n square minus 1. So yes, that gives a nice characterization of CP semigroups. So that's the, yes, so as I said, the previous proposition says the semigroup is completely positive if the submatrix starting from ij2 to n square, that is n square minus 1 by n square minus 1 submatrix, is positive. So it can be written as in this form, that is, if a matrix is positive, then I can write it as a sum of some ak star summing over the index k. And if you just go by the coefficients of such matrices, then we can write it in this expression. And then we plug in this expression in this decomposition of phi here. And we do a rearrangement of terms. So we plug in this value here in this expression of dij here. And then we have regrouped these terms to express the phi x as wx, xw star, and some cross representation of vrp x vrp star. So this is already another form of Lindblad-Gorini-Kossakowski-Sudarson's theorem. So which says that and a version says that semigroup of completely positive maps will have the generator in this format, the wx xw star, with a completely positive map. So because this is a cross representation, so of course this is a completely positive map here in this term here. So this is a version of also LKGS. In fact, with a little bit of manipulation here, we can also come up to this Hamiltonian term and retrieve back the original LKGS theorem. So that was the motivation, and we can also retrieve that result from the general theorem. So yes, thank you very much.